Okay, so we're starting with the problems from yesterday, and I'm giving time right now for you to look at them and solve. I just started the video, that's why the recap of what I just said. So I'm going to give you 30 more seconds, and then we'll talk about what you guys have. Maybe I'll have a few of you, I'll call on you for answers. Or maybe let's have some of you come up and put your work up on the board. That would be fabulous. You guys are already done. Jason, could you do the first one? There are actually tons of markers right here on this desk. You can grab one. Luke, how about you take the second one? Tyler, you cool with the third one?
You showed us in class yesterday.
I did, but let's throw it back up there just for the sake of looking at it. Joe, how about you do the fourth one? And then, Emma, how about I give you the fifth one?
Wait, no, because it's odd. Yeah.
Alright, so from what we can see on the board, when a function is continuous, the limit is the value of the function. That's at the points where the function is continuous. So what we've been doing is direct substitution. We're saying, okay, the function's continuous at that point, so the limit is going to equal the function value. When there's a discontinuity, we have problems with that. Because maybe the function has a value here, but there's an asymptote in the graph at that point. So the function looks like it's going up to positive infinity, but the function value is this value right here. The limit here will not equal the value of the function. Similarly, if we have a jump discontinuity, there's a value of the function, but it does not equal the limit because the left and right don't match. And if we have this oscillating function, this jumps up and down so much it can't make up its mind, and no matter how much you jump in, what you're going to see is the values fluctuate. And it doesn't happen with a lot of functions, but it happens with some. And within this crazy spiral, the more that you zoom in, just the more pronounced these things become. It's kind of nuts. So this is going to be an issue where we don't know what the left and right hand are. We can't figure it out because every time we zoom in, it changes. So we can't figure out what the limit is. These are the three situations for where the limit does not exist. Now, of course, I could put no value here. I could put a value up here. You know, it doesn't really matter. The point is the left and right hand limits don't match each other. And over here, although there's probably a value at a specific point, actually there's no limit because we can't tell where it's headed. So that's kind of a weird thing there. So here, all of these functions are continuous at the point that we're looking at. Are all of these functions continuous?
Yes, no.
I'm hearing yes and no. Is this one continuous? Yes. And the domain here is actually negative infinity to infinity, right? Because this x squared means if I take any negative number and put it in here, it becomes positive. You add 4. There's no way to make this a negative integrand. So we can use any x value we want. There's not a restricted domain. Now the range might be affected. Okay, I'm going to have to take this, so just hold that thought. Hello, Mr. Rigger. I sure do. Yeah, I could do that. Yep, bye. Alright, Brian, you got to head up to the main lobby. I'm going to give you a pass from Mr. Rigger to oh, well, we're going to pretend like that's a whole pass through. Okay. So, this is continuous. This is a cubic root, so it doesn't matter, cube root, so it doesn't matter if there's a negative in the integrand, because you can get a negative number when you cube. Here, tangent x is sine x over cosine x, so wherever cosine x is 0, we have an asymptote. So this is not continuous. This, there's no denominator. This is going to be continuous. This is going to be continuous. So this is the one that's not continuous. But that doesn't mean it doesn't have a limit. It just doesn't have a limit where cosine is 0. Now don't get confused with cosine of 0 and cosine is 0. That slight terminology might throw some people. So here we're just going to throw 2 in, or no, 0 in because we're going to 0. So 0 squared plus 4. We're going to actually not get plus or minus 2 here. Why not? Emma?
Because you can only take limits of like functions.
Well, not. We've only been taking limits of functions. This doesn't have a plus or minus in the front. When it doesn't have a plus or minus in the front, we're assuming that it means the principal root, which is the positive root. If there is a plus or minus in front of it, then we know we want both roots. If there's a negative in front, we know we want just the negative root. If there's no sign, we're assuming they want the principal root. Now, that's different than when you're solving. If you have, whoa, good video footage there. If you have y squared equals x, and you're solving, when you take the square root, you know, then it's the practice that we do plus or minus. But if they're already giving us this, we don't add a plus or minus sign. You see the difference of the technique there? So this was almost right, and you would get most of the points for that. But you wouldn't get them all, because you would technically be telling me an incorrect answer. So just 2 there. Over here, we throw a 3 in, and we get 2. Let me just make sure that's what I got. That is what I got. So if my paper says it's right, it's got to be right, right? Now sometimes I make mistakes with my paper too. Okay, so we plug 3 in. Over here we plug 0 in. If you don't know your trig, you got to know it. This is something that we have to get down, because I'm going to assume you know it. But I also know that sometimes we have weak spots. So I am going to give you friendly reminders as we go, but I'm going to hold you fully accountable for knowing it at the same time. So I'll give you a little quick trig reminder right now. This is, yeah.
Do you have unit circles you can make out?
You know, I was talking about that. I can print some. Let me make a note for that. But I'm going to show you something that might eliminate the need for this.
It'll blow your mind.
Did you guys like it? Those of you who had me for freaked out?
4, 3, 2, 1.
Yeah.
I love that.
Okay. So, unit circle. Alright, this is something that somebody taught me and I adapted it a little bit. They taught me if you can count to 1, 2, 3, you can know 30, 60, and 90, or 30, 45, 60. And I realized, Well, if you can count from 0 to 4, actually you know from 0 up to 90 degrees. And then that's the whole first quadrant, and then if you know how to use reference angles, you can kind of figure out the rest. So, sine of theta, cosine of theta, and this is going to be theta. You guys all know theta, right?
Theta.
Yeah?
An angle
Okay.
measure.
Yeah.
It's also
Okay.
a letter.
So, this is going to be our reference angles, 0, 30, 45, 60, 90, or 0, pi over 6, pi over 4, pi over 3, pi over 2. Okay. Now, if you want a quick way to remember these, what do you multiply this number by to get to 180? So 90 times 2 is 180, so that's pi over 2. 60 times 3 is 180, so pi over 3. So that's a quick way you could remember that if you have trouble remembering those things. Now, here's where the magic happens. 0, 1, 2, 3, 4, 4, 3, 2, 1, 0. Now we have to do some magic here. We're going to
It's magic.
square root the top, square root the bottom, and then throw them all over 2. So, square roots, and then over 2, over 2. Alright, so this is kind of a really quick thing that you can generate that will help you with all the reference angles. 0, square root is 0. So this is 0. This is just 1/2. Root 2 over 2, root 3 over 2. This is 2 over 2, which is 1. And then the same thing backwards. 1, root 3 over 2, root 2 over 2, 1/2, 0. So really, if you just have to count, 0, 1, 2, 3, 4, 4, 3, 2, 1, 0. The way that this works is because of the sine, cosine. These are co-trig. Sine, cosine. They are complementary. So whenever the angles add to 90, 0 and 90, they must be the same. So 30 and 60 are going to be the same across. So that's kind of why we get this nice relationship. And then you pair this with your 0, pi over 2, pi, 3 pi over 2, 2 pi. All students take calculus. This will give you the reference angle. This will give you the sine in any quadrant. And then you don't have to memorize the entire unit circle. You just have to know these and then know where to place it. And then what sign it is. So you're going to see me reference this a lot. This has really revolutionized the way I do trig in terms of the speed with which I do it, because now I'm at the point where I can visualize it on the chart. Say, okay, well 30 comes first, so 1/2 for sine. So it's just something that has really helped me a lot. So what about tangent? Tangent is sine over cosine. So again, this is nice and easy. Tangent theta, since they have the same denominator, it's just the numerator over the numerator. So this is just 0 over square root of 4, which is 0. This is root 1 over root 3, root 2 over root 2, root 3 over root 1, root 4 over root 0 for tangent. And then you might have to simplify that, but when you want the reciprocals, flip them. So cosecant, secant, and cotangent are right there too. So I find that this is a very useful table, and when somebody showed me this, I couldn't believe, like, wow, that made such a big difference for me. I can still purchase you guys some unit circles, but for me, I found this to be really helpful in some ways that the unit circle never was for me. And the unit circle tends to rely on memorization, whereas this makes you think about how are they related to each other, which helps you do the whole mental math and understand the relationship between the trig functions a little better too. Yeah.
Did you teach Mrs. Garber that?
I did show her that, yeah. Did she show it to you guys in class? Yeah. So I'm going to keep referencing this, but I will give you some unit circles. Because some of you might say, I just like to memorize. But I'm going to tell you this. Memorization is a nice tool, but sometimes it's better to know how to think your way through a problem than just have something memorized. Because if memory fails, you can't think yourself through, how do I remember that memory that I don't remember? You know? So I'm going to sometimes challenge you guys to get away from the traditional memory tactics. There are some things where you're just going to have to memorize. There's no way I'm going to ask you to derive every time, what's the derivative of inverse tangent? And you don't know what any of those words mean right now. Well, I guess you know inverse tangent, but you'll see. This stuff gets messy, and you're just going to have to memorize some stuff. But other stuff, I'm going to challenge you to think through. Okay, so this one, we're going to directly substitute pi times cosine pi. Now, here we have to know, cosine is the x value. So, we're at pi. This is negative 1, 0. So that's negative 1. That's pi. That's negative pi. So for the axes here, it's really just going to be 0, 1, or negative 1. You just have to figure out, are we talking about x or y, cosine or sine? Tangents, sine over cosine, so you can always, So if you remember tangent, sine over cosine, you do less memorization and more, okay, let me see how these are related. And over here, sine of 0, 0, sine is the y value, and at 0, y is 0. This is 1 comma 0, that's why that's 0. At 0, cosine is 1, because we're at the point 1, 0, and cosine calls for the x value. So that's how I'm going to keep referencing drawings like that whenever I do trig. I find drawings to be very helpful in organizing information, and that's one thing I want to help you guys get better at is organizing your information so it's workable and understandable. Alright, so now that we've done this, let's jump to part 2. I know it's riveting, right? I can see the excitement on your faces, particularly in the back corner there.
You should just have something on part 1 that just says to be continued.
Bum, bum, bum. Alright. This is not going to be new news, what we're about to say. Direct substitution doesn't always work. Because sometimes we're going to be asking for something where there's an asymptote or a discontinuity, and the function might not exist there. So, if the function doesn't exist, does that mean the limit doesn't exist? Not necessarily. We've already talked about that a little bit. So, we're mainly going to be thinking about this in terms of this type of problem, a rational problem. So, I have a rational function there. Why can't I put 1 in? Right, because I'll get 1 cubed minus 1 over 1 minus 1, which is 0 over 0, which everybody knows is 1, right? No. You cannot divide by 0. Oh, I don't know what kind of spelling that was. You cannot divide by 0. So, don't fall into that trap. Oh, the number over itself. Sometimes we're doing stuff so fast we just don't even think about it. So make sure you're looking at what you're looking at. You're seeing what you're actually seeing, not what you think you're seeing. Sometimes we you know how you read with your brain, not with your eyes? So sometimes how many F's are in the sentence and everybody gets it wrong? Do you know what I'm talking about? Where it's of all the free food of the farmer, and it's a sentence. People catch these F's because they make the F sound, and they ignore these F's because they make the V sound. So when you're asked to really quickly count the F's, people are going to be like 3 instead of 5. And they're better examples than this. I just made one up. But we do the same thing in math. We expect to see something based on what we have seen, and we ignore what's actually there. So make sure you're really looking at your numbers and your algebra. Don't try to cancel things that don't cancel. Because you're going to have some stuff where you're going to say, you know what? That's an x plus 1, that's an x minus 1. Cross, cross. No. You can't do that. They're not the same. Don't cancel them. So make sure you're being careful. All right, so what does this graph look like? What kind of graph is y equals x squared plus x plus 1?
Parabola.
It's a parabola. And it looks a bit like this. Now, what does this look like?
Parabola with a hole in it.
A parabola with a hole in it. So, if you don't believe me, get out your calculator, graph it. We've got time. Let's everybody do it. You know what? I'll even do it. I'll do it on the board. Everybody. Calculator party.
Do them at the same time or do them separately?
I'm just going to do the, you know what? How about you do them at the same time? I'm going to change to the color version here. And I'm going to clear. Make sure you put this in with the right parentheses or using that numerator thing, otherwise you're going to end up with the wrong graph. Okay, x cubed minus 1. Oops. Be careful if you're using the power button, because it will keep you up in the exponent, and that's a good way to accidentally type in the wrong thing as well. Alright, so this is what I have, and I'm going to have to, you know what, I'll make this a little smaller. If I can. No, they're not going to let me. Alright, well. I graphed in blue and red. Blue first and red second. And the red is totally on top of the blue, so it's the same graph. Let's look at our table. So I'm going to have to zoom out. So I'm going to go to my table, and I'm going to check what happens at the value x is 1. Error for the red one. 3 for this one. So we do, in fact, get the same graph, except this one has a hole right there. Why? Because you can factor x cubed minus 1. It's a difference of cubes. So, x cubed minus 1 over x minus 1 is x minus 1, x squared plus x plus 1 over x minus 1. Which gives us this canceling effect. Which means it's essentially this graph, except we still are not allowed to let x be 1 because of its denominator. This is the type of problem we're going to be looking at in part 2, where we have potential problems. Either there's an asymptote or there's a hole. Go ahead and work on this one with a partner. X squared plus x minus 6, x plus 3. It is minus 6. If you have a plus 6, this is not going to work. It's not going to be the same.
Now it's the same.
Alright, so let's take a look. Some of you graph this. That's a fine way to look at it, to see what is this graph going to look like. Hopefully what you saw is a line, x minus 2, y equals x minus 2, is going to be the line your calculator will graph. Yes? Because for all points except x is negative 3, this graph is y equals x minus 2. And it's undefined at x equals negative 3. So, this is y equals x minus 2, so we're going to go down. This is our graph. Now, what does it look like the limit is going to be here? It looks like it's going to be the value of the line at that point, right? So, instead of plugging it into this, we directly substitute into what's left over. We put negative 3 into this, which is the same function except for a point or two, usually, if we have to cross out a couple things. So, what is negative 3 minus 2? Negative 5, which is what this limit is. So, this is how we're going to handle these problems. You are going to first algebraically simplify. X plus 3, x minus 2, x plus 3. Don't forget your limit sign here. These will cancel, which means that you're taking the limit of x minus 2 as x approaches negative 3, which is then negative 3 minus 2, which is negative 5. This is how you're going to approach these problems. Yes?
So just clarifying, in calculus, when we're working with limits, we can cancel things like that without making...
As long as they cancel, and there's not a repeat factor down here that would make it so that there's an asymptote. They're the same exact function except for that point, and we're looking at a limit. So when we're looking at limits, yes, the limit will be there. But we're going to have later things that say, this only works if it's continuous. So you're going to have to be careful with the theorems. Some theorems only work if it's a continuous function. And this is not a continuous function, though it looks just like one. And your calculator isn't going to show you that dot that's missing, because it can't. Does that make sense? So in calculus, yes, sometimes we're allowed to say, you know what? That is essentially this, so we're going to use this to model our situation, rather than this. But there are going to be other times where discontinuities are going to mess us up. Everybody good with what we're doing here? Yeah?
You can just write limit of x as it approaches negative 3. We don't have to do it from the right and from the left.
Right. So this is what we're assuming. When we're saying the limit, we're kind of taking into account both at the same time.
Okay. But we don't have to write both.
You don't have to write both. There might be some times where we say, verify that this limit is negative 5 by using the left and right hand limits, in which case you would say, well, the limit of this function as x approaches negative 3 minus from the left is negative 5, and it's that from the right too, so therefore left and right do equal. So this implies that the left and right do equal this, but you don't have to write it. I know that's a long answer for your question, but I want to make sure we all understand the implications of this. Whenever we have a limit without a left or right, it means both equal what this equals, if it exists. Okay, let's keep rolling. So, the question here that you reason through is, generalize situations for which this technique would help you determine the limit of a function. When can this technique help you find the function when there's a discontinuity?
When there's a numerator and a denominator of 1 less power.
So, what really did we do here? What if I would have had this? Here, this has a bigger degree than this.
I guess you just.
If I cancel this, I get 1 over x plus 3, and now directly substituting in a 0 is not a problem, right? So it doesn't necessarily have to do with the degree. What does it have to do with?
Can you cancel?
Canceling a factor. Canceling the factor that makes the limit have a 0 in the denominator is going to be when you can use this technique. So you can write that in your own words here, because that's going to be something we're going to be using a lot. Okay. So, now we're going to be talking about rationalizing. Rationalizing is not a new concept. We learn about rationalizing when we have like 1 over square root of 2 and we say, oh, radical in the denominator, that's bad, right? So how do we fix it? We multiply the top and bottom by root 2, right? So we get the radical out of the denominator. What if I have 1 over 1 plus root 2? 1 minus root 2, the conjugate. Because if I multiply by 1 plus root 2, I get 1 plus 2 root 2 plus 2. And I still have a radical in the bottom. But remember, the conjugates make it so that you lose the middle term. You just get the square of the first minus the square of the second. So we're going to multiply by the conjugate. The thing is, here, we're going to do this a little bit differently. Instead of using the denominator and saying, you know, we have to rationalize, we're going to rationalize the numerator for the sake of getting more terms in the denominator so that we can plug a 0 in and there won't be a problem. So, if you guys want to know these blanks, when the radical's in the denominator, you multiply by the conjugate, but we're going to be rationalizing by the numerator, rationalizing the numerator to help us. So this is where calculus gets hard. It's not the calculus, it's the algebra. So, what we're going to do is we're going to rationalize this first, and then take a limit of that. So, but to rationalize, we have to multiply by the conjugate. Be careful, the conjugate is not square root of x minus 1. It's what's in the square root, opposite sign, and then the thing that's not in the square root. And we have to multiply the top and the bottom by that. Woo, that was too fast. Alright, we will pick this up tomorrow. This is kind of algebraically heavy, but this should take like 5 minutes tomorrow. I'm still going to collect that homework on Monday, because you can do all but like one problem, and this is in your book. And at least now you know the setup.
I'm
So-
very curious about the 2 policemen and a drone theorem.
Yes. That's a pop math culture name, that's why I put it there. I do not, of course, support anything about being drunk. And actually here, he's being accompanied by 2 policemen because of his behavior. So,